Okay, so I'd like to welcome everyone to this installment of the EuMA webinar series. In fact, the first of our webinars in 2025. I'm very happy that we have the chance to start the series again and to continue with it. So just to introduce myself very briefly, my name is Jan Barowski. I'm with the Institute of Microwave Systems at University of Bochum in Germany, and yeah, as part of the Young Professional and Innovation Team and the European Microwave Association, I'm very happy to have today with me Paul Chama and Aarón García-Luque, who took part in the, or very successfully took part in the Tom Brazil Award competition in frame of the European Microwave Week. And yeah, both of them will introduce their research and their ideas and themselves to us. And I'm really looking forward to this. Before we start, I'd just like to share with you a few slides and a few comments on the next European Microwave Week and this webinar series. So, as I said, first of all, the most important part, people today, I'd like to very briefly introduce Aarón and Paul, who will give us two talks on first on the design and development modeling of a new generation of semiconductor-based active devices for high-frequency reconfigurable applications. I'd like to welcome you, Aarón. And afterwards, we will have Paul, who's doing a deep dive into the potential of indium phosphide mimics and chiplets for radar front ends at very high frequencies. Welcome to you, Paul, as well. Yeah, just to give you an idea, so both of them, Aarón and Paul, took part in the Tom Brazil Award competition in frame of the European Microwave Week. Yeah, one of Europe's largest events in yeah, microwave engineering and microwave research. I'm sure most of you know. So the Microwave Week this year will take part in Utrecht at the mid and end of September, and consists of three major conferences: the European Microwave Integrated Circuit Conference, EuMIC, the European Microwave Conference, UMC, and the European Radar Conference, EuRad. And for those of you who are students or doctoral students, there are a lot of events I really can recommend to you from own experience. There are design schools, there are schools on signal processing, there are young professional events and a career platform. And yeah, there's also a party I've heard rumors of. So it's really a good thing to be there if you're interested in microwave research. If you like to contribute to the conference yourself with an abstract or a talk or a poster, there's still this chance to do your submission until 11th of March. Yeah, special focus or a special program I'd like to highlight is the volunteer program for those of you, again, who are students, especially also undergrad students. There's a chance to help out at the conference, doing some work there, and in return get some benefits like free access to our conferences. You can stay up to 7 nights in a local hostel to have the chance to yeah, to be in Utrecht all the time. And yeah, that's also from personal experience. I really recommend this to you. That's a good chance to visit one of the major events in our area. Yeah, especially focus today is on the Tom Brazil student essay competition, where Aarón and Paul were very successful with. So the Tom Brazil Award is featuring a specific topic where you are invited to ask to submit an abstract on the topic of advancing sustainability in or through microwaves. The award is open to all students enrolled in a full-time Ph.D. or a graduate degree program within the field. And also the same deadline holds. You can submit your abstract until 11th of March. Yeah, to this email address here, and it's it's really a nice thing. There are great prizes which are sponsored by the gallium arsenide application symposium. Okay. Last but not least, I'd like to do some advertisements for our last webinar talks that we had. So we already had a few. There's a YouTube channel provided by the Microwave Association where you can have a look on the topics that are of interest to you. And I invite you to join us there. Okay. So enough with the advertisement. So today we will have, as I said, two speakers. We will have Aarón first, talking about his research, and afterwards Paul will do his talk. All of you will have the chance to ask questions to the panelists right after their talk. So I'll try to moderate this a bit, and yeah, looking forward to this. So then I have the pleasure to introduce to you Aarón García-Luque, who received his bachelor's and master's degrees in telecommunication from the Universidad de Málaga in 2018 and 2020, respectively. He is currently pursuing his Ph.D. with the Telecommunication Research Institute in Málaga. He was also successful in our EuMA internship award program, doing an internship at the Institute of Robust Power Semiconductor Systems in Stuttgart, Germany. And his research is mainly focusing on nonlinear modeling of semiconductor-based active devices, including diodes, varactors, gallium nitride transistors for microwave and millimeter wave applications. And his talk today is on the design and development on modeling of a new generation of semiconductor-based active devices for high-frequency reconfigurable applications. Welcome to you, Aarón. The stage is yours, so I'll invite you to share your screen, and I will close my view here. Okay.
Okay, so thank you very much for your introduction, Jan. Firstly, a very warm welcome to our audience. Good afternoon, everybody. And for me, let me tell you that it's a truly pleasure to be here to accept this invitation from the European Microwave Association and to collaborate in order to spread telecommunication, research, and scientific projects around Europe. So for me, it's a truly pleasure to be here. I am going to share my screen. Okay, 1 second. Oh, okay. I think right now it's okay. So, in the next few minutes, I would like to introduce our latest work on the design, development, and modeling of a new generation of semiconductor-based devices for high-frequency reconfigurable application. Let me say that the idea under this speech is not a very technical overview, but also to provide a general overview of our latest work and to persuade and encourage young students, young audience specifically, in order to take the opportunity to travel around Europe and to try research. So I'm going to activate this one. Okay, so not too much time about my presentation because I really appreciate the introduction that Jan gave about myself. My name is Aarón García-Luque. I am right now a Ph.D. candidate at the University of Málaga, more specifically at the Telecommunication Research Institute. And about my career, I have been in recent years working in diodes, varactors, transistor, large signal, and our latest work, the idea which I bring you today on the non-quantitative modeling of these devices. I have been involved in several papers, and indeed I would like to share my overview about the EuMA Internship Award, which I have fortunately the opportunity to enjoy years ago. So more or less about a little bit of context, our modern RF paradigm has changed recently in recent years, in which the requirements in terms of latency and bandwidth forced to novel solution reconfigurable using tunable properties of several surfaces. For example, novel reconfigurable interior surface are really interested in the novel context. Indeed, the possibility to use nonlinear vector network analyzer and modern circuit simulation tools offer the possibility to solve the classic problem of using linear solution as S parameters in this modeling. In particular, the solution that we bring today is a model for one-port devices. For example, these kind of varactors or pin diode devices are playing a key role in novel reconfigurable surface. So the idea is, if we are allowed to offer a very good model in large signal and high frequency of these devices, we will be able to control these tunable characteristics in a software in a remote way. So this is a little bit about the motivation. Moreover, higher frequency challenge lead us to the problem that relaxation time, which mostly of these semiconductor devices suffer when the bias conditions are instantaneously changing, must be also be considered. So if we try to offer a more or less overview about modeling possibilities, it is a good way to divide and split the nonlinear modeling technique into two main groups. On the one hand, black box modeling techniques usually offer the possibility to give a model based on experimental result. For example, lookup table in which a vector is provided from this current and voltage measure. Typical neural network processing is also something which right now has attracted the interest of a very deep scientific community, often a very learning and parallelism skill, but suffering overfighting and computationally expensive cost. And another possibilities are X parameters, which is a technology independent and automatic, which offer a good performance, a good validated performance, but in which the bandwidth on frequency domain is critical for this design. The solution that we offer is an analytical model in which we will build a circuit whose parameters depends and are extracted from the terminal current and voltage measurement. So the lineup for today is talk a little bit about this introduction, present the extraction technique in which we are going to develop how this novel quasi-static and the non-quasi-static version of this model, how this one can be extracted, and how this work can be related with the priceless opportunity of the EuMA Internship Award, which I was enjoying in 2020, 21st, and small details about the research abroad. I will finish with personal tips in order to encourage the young audience to follow this speech. So, what about foundry models? Foundry models offers always a very good solution. For example, here we have our varactors foundry model, a typical spike from the model for a Schottky diode, a quick solution, but only valid in the linear region. This must be understood as these models offers a good performance, but not always in large signal and high frequency regime in which novel application must be developed. So, for example, if we try to understand the performance of the devices, here we have two varactors and a Schottky diode, this one, in which several additional extractors were developed for the measure. And if we perform different measures with this kind of commercial devices, I am showing you right now the setup for the phase calibration, for the power and vectoric calibration. We are going to study the S parameters performance of these devices, and the waveform performance in terms of current and voltage. The idea is verifying if the non-quasitative phenomena appears at high frequency and if the possibility which offers this non-quasitative model is really good enough to be considered. So if we study firstly the performance of this commercial foundry model, we can see, for example, in S parameters and in voltage and current waveforms that if power increase a little bit or frequency increase a little bit, the performance is not proper enough, only allowing a good behavior in a few units of gigahertz. The same is for the Schottky diode. We have here the performance of S parameters at the same for nonlinear waveform. Indeed, if we pay attention to G and H graph, we can see that with non-sinusoidal waveform, the performance of the foundry model is really far for a proper behavior. So the model that we present today in order to overcome this limitation are composed of a conduction current source and an electric charge current source. This one offers that the total current of the device is the direct sum of the conduction and the displacement current. So this current must be understood as the direct sum of these two parts, in which this one, which is associated with the resistivity phenomena, must be a quasi-static magnitude. This means that voltage, bias condition, instantaneous change offer an instantaneous response in the device, and this electric charge must be considered quasi-static or non-quasi-static depending on the version of the model. This equivalent circuit for one-port devices overcome several problems. For example, models which is typical modeling about S parameters, which only allow a partial exploration of the voltage domain due to self-heating of charge trapping effects, or improvement versus another pulse measurement typical setup, which are really tedious and require a very robust equipment and very far away from typical continuous wave regime in power amplifiers. So the direct extraction of this robust and CAD compatible model must be presented right now. Firstly, we present an extrinsic network in which we try to model all the behavior of the package in order to provide a good behavior in high frequency. For example, at low frequency and reverse bias, the path capacitance at the C part capacitance, this offset must be extracted according with this procedure. And at low frequency and forward bias, it is directly estimated this series resistance as the approach a very large bias condition. In this way, these two kind of procedure offer us a solution for mostly of the extrinsic linear network which has been considered. We are not going to enter into much details because I will provide you the paper reference, but according to an algorithm, it is possible with an optimization tool to extract the behavior of this inductance. So we have the extrinsic model. Let's move on to the intrinsic circuit, which is more interesting and which supposes a more difficult challenge. So firstly, for the quasi-static model, we have these two sources, the conduction resistivity part, and this first derivative of the capacitance, which is associated with the capacity phenomena. And this is the procedure. We're not going to go into very details about the process, but from a large signal singleton acquisition, it's going to be possible to extract this magnitude and this one according to this procedure based on the current balance previously introduced. But unfortunately, all the equations are not enough to solve the problem. If we extrapolate the challenge to the non-quasi-static model, we have this first order equation in which appear a quasi-static delay function and an electric charge quasi-static delay function to provide this non-quasi-static electric charge, and the same procedure is repeated. The key factor in order to solve this problem is which is called the nonlinear function sampling operator, which offers an additional set of equations in order to establish that a spectral coefficient of the quasi-static magnitude, real and imaginary part of those coefficients, are related if we perform a discretization in which each sample of the voltage domain can be divided into several intervals. This means that sample A, B, and C will be the same point in the voltage domain by performing this approximation which leads us to an overdetermined system, which, for example, can be solved by least square algorithm, and which give the solution to this extraction problem. Once the problem has been extracted and formulated, let's move on to the implementation. Here we have the ADS circuit, in which this equivalent circuit with the full extrinsic network has been extracted. The capacitance of C represent the extrinsic model of the quasi-static device, and the orange trace is the non-quasi-static version of the circuit. So here we have the non-quasi-static version versus the quasi-static version. Indeed, for example, if we pay attention to several extractive magnitudes, we can see, for example, that the resistivity current of the quasi-static model is quite different, for example, to the typical Schottky law, which is used to model this exponential behavior of the typical resistivity phenomena current. Indeed, in varactors, which are devices we only or more often are dedicated to work under negative bias condition, we can approach that this current is negative. And if we pay attention, for example, for two kind of varactors in this capacitance of an indeed delay, we can see how those magnitudes has been extracted and implemented in the model. So let's move on to the experimental validation of the model, in which, for example, if we pay attention to the S parameters graph and this behavior in the C graph versus the bias condition, we can see that the non-quasi-static model offers a better performance than the quasi-static, and obviously a much better behavior than the foundry model. Those results can also be extrapolated into the waveform. For example, if we pay attention to this foundry graph, we can see that can be improved rather than the quasi-static and the non-quasi-static waveform, and the same for the varactor. Indeed, two important conditions and two important conclusions of those results are that, firstly, even in S parameters, it has been demonstrated how the behavior of the non-quasi-static model is better than the quasi-static one, and if the operating frequency is increased, for example, to 8 GHz, it has been demonstrated how the non-quasi-static behavior is much better than the quasi-static ones, giving the reason in the idea that non-quasi-static phenomena must be modeled as rising the frequency. So if the operating frequency is higher, those phenomena must be considered, and only a model which takes into account this time constant offers an overall good performance. So this has been more or less the work in which I have been involved in my local university here in Spain. Another additional works, for example, if we take only partial information, not considering all the bias domain, we can also see that the performance of the non-quasi-static model, for example, this one is taking into account the cross correlation of the signals, which maximum must be 1. At different frequency, but specifically at 8 GHz, has been demonstrated how the non-quasi-static behavior is always the better solution. And this one-port solution also has demonstrated how only if the discretization in voltage is good enough, we have an appropriate extraction. So those results has been published in last years in several papers. This is from one magazine, this is from one conference, with really, really good results. But this work must be completed and can be extended with the priceless opportunity that I have in 2021 in Stuttgart, thank you to the European Microwave Association, in which I have the opportunity to work and to stay in the Institute of Robust Power Semiconductor System under the supervision of Professor Irma Kalfas. These are several pictures about the facilities in which we were working with several gallium nitride transistors in collaboration with INM Chips, which is a foundry which was allocated there and allow us the possibility to directly manufacture all devices done in a very good, in a very quick way. So the work there, in which the state of the art of gallium nitride must be a little bit understood, is at the industrial way, always this kind of manufacturers are trying to reduce cost and to offer a good overall performance. So, for example, in novel transistor, the decision of the substrate, here we have several performance and figures of merit with diamond, silicon, carbon, silicon, silicon, is a key factor. So our work there was the idea to show up how high resistivity silicon is becoming a popular substrate due to its low cost and low loss properties. Indeed, if a more cheaper substrate is developed with similar performance that, for example, silicon carbide and diamond, this allows in the industrial way to reduce a lot of cost and to overcome a little bit the producing procedure. So, for example, this is a picture in the clean room of INMs. I am the blue guy here. Not too much detail about the processing flow in which the initial structure, mesa formation, after all, the top layer passivation, and how the procedure going on with the OMI region, the recess and dielectric deposition, and the final gate and pad metal deposition. I'm not going to give too much details about this opportunity, which I was allowed to see as directly in person there, but I am going to point out a couple of details about the OMI optimization process there and the different gate dielectric deposition and performance. So, for example, the procedure completed there allowed a very good performance in terms of resistivity. For example, this is the map for the sheet resistance with the TLM method, and from the clean resistance of the structure, those resistance offer a very, very good uniformity, and moreover, several additional studies give us the information about, for example, how the transconductance of this of several barriers offer different performance, the threshold voltage for several technologies, and, for example, giving us the possibility to understand results like gallium nitride argon is better than another technology for different conditions, maximum transconductance, and this specific threshold voltage point. All these studies was the best way to trying to develop a mature technology properly for new development in terms of the novel gallium nitride context. More or less, the specific work that was developed there, this is the CAFIL structure which was developed, was based on several argon transistors. In particular, different structures were developed in order to measure the performance and several figures of merits of those transistors. For example, this is a microscope overview of these transistors. This is a picture of how those ones were measured with the wafer system, and all these structures give us the information enough to confirm that the manufacturing procedure was good enough. Indeed, this work offered a good performance, even better than another similar technology from another foundries with more classical substrate, allowing the possibility to say that this high resistivity silicon substrate offer a very good performance in terms of, for example, transconductance or breakdown voltage. My committee there was trying firstly to develop a small signal model of this transistor in which, considering all the effects of barrier, channel, buffer, and substrate, this give us this model in which extrinsic and intrinsic parameters must be considered together with gate to source and gate to drain resistance for gate leakage, and all this procedure give us the possibility to develop and to understand the different parameters of these models. Indeed, after the S parameters multi-bias acquisition, path capacitance, inductance, resistance at the intrinsic circuit was developed. The idea was to offer a small signal proper model in order to extract the figure of merit of this manufacturing procedure and going on in an easy and quick way to evaluate the performance of those new transistors. So, for example, extrinsic capacitance were extracted at cold pinch-off condition under this linear approach in which inductance and channel behavior can be neglected. This is the linear behavior, so what for those measurements. Extrinsic inductance and resistance in a very deep procedure by considering that resultant inductance and impedance are considered as channel resistance. Those equations give us to this linear behavior in which from these S parameters, by considering that channel resistance is neglected, offer us the possibility to extract those inductance and those channel resistance, and the intrinsic equivalent circuit in this 10 parameters circuit can be extracted by this analytical procedure together with a de-embedding process from the S parameter measure. So according to the performance which was observed, for example, here I'm going to show up the result for this transistor of gallium nitride, and from this one from gallium arsenide, we can see how the equivalent small signal circuit was implemented in ADF with those parameters with very good perform in terms of a very few mean relative error in a bandwidth in up to 38 gigahertz, showing up and demonstrating how the equivalent circuit offers a very good overall performance. Moreover, typical linear behavior in a proper frequency response, for example, for the resistance at the capacitance, allows that the extracted circuit was robust enough in order to those conclusions. Moreover, in order to going on with the large signal circuit, the bias dependence of several parameters was also extracted. Indeed, if we pay attention, for example, to gain characteristics of the device, we can compare the performance of this high resistivity silicon device versus, for example, silicon sapphire, gallium nitride sapphire, or another technology offer, even in several cases, better result with a very mature technology. So, in order more or less to sum up all the work that was done in this at the moment, the small signal circuit is ready and is tested and prepared for try to extrapolate the one-port modeling technique shown in the first part of the presentation into the second part. Indeed, it also be possible the integration of this novel transistor into novel RF power technology, and varactors and pin diode are key factors in the model and develop a new reconfigurable solution. So this modeling technique can also be useful in several reconfigurable device developments. Last but not least, I would like to finish this small speech with 3 personal tips about my priceless experience in Stuttgart, in which not only my professional but also my personal career was completely changed. The first one is I would like to encourage our young audience to apply to this kind of priceless opportunity, because learn from others is the best way to improve our knowledge. I learned that get out of your comfort zone and discover new places, new technology. For example, in mostly countries, industry and manufacturers are really advanced, and it's a priceless opportunity. And lastly, I would like to say that keep yourself updated is the best way to going on with your career and to improve yourself a little bit more and more. So basically, with this small summary, I have finished my presentation. I really appreciate your time and the opportunity to the European Microwave Association. We will going on publishing all these kind of results. And at the moment, we are really satisfied and really looking forward to seeing if this one-port equivalent non-quantitative model can be useful also with transistor, in which part of the work has been already done with the small signal circuit. So that has been all from my side, and I am at your disposal for any question and any curiosity. Thank you very much from my side.
Yeah. Thank you, Aaron, for this very interesting talk. It was quite a lot, so I'm totally not into large signal and hardware modeling, but it was very interesting and very enlightening. Thank you for that.
You're welcome.
For our audience, I just put a note in the chat, and I'll just state it here again. You have now the chance to interact with Aaron and to ask him some questions regarding his work or maybe his personal experiences, whatever you like. Please use the Q&A panel that we have for that, or the chat window. So I'll be happy to forward your question then to Aaron, and yeah. Oh, there's a question from Jess. Do you see this being useful for other diode types, such as pin diodes, for example?
Okay. So at the beginning, the idea of this model has been developed in a general way. So we have been trying with varactors, with Schottky diode, still not with pin diode, because this specific kind of diode must be considered with their specification. But the idea to offer a general model is try to see if the behavior can be adapted into each kind of technology. So in newest work, probably we try to adapt the solution to pin diode, and to see if the behavior is good enough, because obviously pin diodes are one of the technology which is required in novel reconfigurable devices.
Yeah. Maybe in the meantime, I have a question regarding the behavior or the modeling of harmonics that are introduced by a nonlinearity. So is the nonlinear behavior that you model on the fundamental tone by S parameter measurements and by S parameter measurements at different bias voltages, is it directly related to the power level of the harmonics? So can the model be used for that as well?
Indeed, this one has been one of the bottleneck of this measurement procedure, because for example, if our network analyzer reach a specific bandwidth, we're not allowed to go in very far away in frequency because harmonic are needed in order to the reconstruction of the wave of the nonlinear waveform. But we have observed, for example, in the Schottky diode waveform, in which non-sinusoidal waveform can be achieved easily, that is key factor to consider a big bandwidth in order to have a very good overall response of the waveform. Indeed, the extraction procedure only offer a good solution if a minimum of harmonics are considered in the extraction algorithm. For example, in our test, which has been carried out right now up to 40 gigahertz with this kind of devices, a minimum of 15 harmonic has been required in order to have a proper extraction. Because, for example, if you consider a narrow bandwidth, there is not information enough to solve the problem, and the algorithm give a no proper solution.
Okay, thanks a lot. There's another question in the chat. Aaron, what is your experience with respect to modeling accuracy for memory effects?
Okay, it is true that, for example, church trapping is a little bit far from our study, but in those studies, I can say that, for example, right now we are working in several applications in which, if the operating frequency is high enough, appears a relaxation time that must be considered, because if you change the bias, there is not a direct effect in the behavior. So the first order non-quantitative model has demonstrated how this relaxation time is needed, and only this model, if the operating frequency is high enough, is the solution which offer a good behavior. More or less, in the upcoming work, we are going to try, for example, pulse measurement and another high frequency application in order to see if this, for example, if a 2-order or 3-order model offer a better performance. But at the moment, all the application carried out with the first of the model has been achieved and has show up a good performance, more or less, in these initial studies with the non-quantitative circuit.
Okay, yeah, there's just the appreciation in the chat, right? Thank you for the clear feedback. Yeah, I'd also like to thank you again, Aaron. If there are no further questions now, I'd like to hand over to Paul Chammer for the second talk to Good Day. Paul received his bachelor and master degree from the Brandenburg University of Technology in Cottbus-Senftenberg, Germany, in 2023, and he is now affiliated with the Ferdinand Braun Institute in Berlin and is pursuing a Ph.D. in electrical engineering at the Technical University of Berlin. His research focuses on high frequency and millimeter wave integrated circuits and systems, with a particular interest in advancing next generation communication and sensing technologies. The talk today will be about the development of indium phosphide chiplets for the use in radar applications in the D-band, so between 110 and 170 gigahertz. Yeah, and by this, Paul, I'd like to welcome you as well. I'm looking forward to your talk, and the stage is yours.
Thank you very much. I would also like to welcome all of the attendees here, and I will just quickly share my screen. I hope you can see it. If not, please let me know. Yeah, I will give you like a brief overview of the development of indium phosphide chiplets for use in radar applications, especially in D-band, since that is the current research topic I'm working on in my PhD. My talk is going to be a bit shorter than Aaron's, since I just started my PhD a bit more than a year ago, but that just means we have a nice and early coffee break. So I just want to give you a quick introduction about why D-band especially is becoming more and more popular, and why indium phosphide is an interesting material for integrated circuits. Then I want to present some examples from the literature to give you kind of an overview what's like performance that's already achieved, and to see what's currently possible. Then I want to talk about the development of indium phosphide chiplets at Van Braun Institute, to give you kind of an overview about the process we use, about some of the results that were already published, and some of the work that I did and am doing right now. And I want to then end with a conclusion and a short outlook. Yeah, so as an introduction, so the demand for the usage of higher frequencies at millimeter waves and beyond is increasing since new emerging applications in industry and communications, especially for 6G and, for example, automotive radars, are becoming more and more popular. There are high performance requirements regarding data rate and latency, and also strict design limitations in terms of efficiency, power, and also cost. And this introduces specialized solutions like, for example, 3-5 semiconductors like indium phosphide or silicon germanium, which are required to overcome limitations of current technologies. And there are approaches to combine different technologies to get the most out of their advantages. So why we are using indium phosphide? This graph kind of shows the Ft and Fmax values for different technologies and their respective node sizes. And as you can see, very high Ft and Fmax values are associated with all of these black dots and the pink dots here, which are indium phosphide HBTs and HEMTs. And there are also some other technologies like some silicon germanium HBT devices. So as you can see from this graph, indium phosphide is a very promising technology in that regards, and that leads to big potential for high frequency applications. So yeah, as I've mentioned, advantages are high Ft and Fmax, which basically translates to good transistor performance at high frequencies. Also, a very high efficiency is possible and a high output power is achievable. And since the device has a high breakdown voltage, you can also achieve high linearity. But there are also disadvantages since the technologies are not as mature as, for example, CMOS technologies. There's a lower complexity possible. You have more variations across different shots in the wafer and so on. And in general, technology readiness is not as high. And the associated costs are higher. But there's also the possibility to combine it with CMOS or BiCMOS approaches, which then makes the overall systems more compatible or competitive. So examples from the literature, these are some metrics for published PAs in different technologies. On the left side, you have the power added efficiency versus frequency, and on the right side, the saturated output power versus frequency. And again, as you can see, for indium phosphide devices, you can achieve very high efficiencies up until high frequencies, and also very high output powers until high frequencies. So that again shows that the technology offers great potential for this. Some prominent examples from the literature are from Zach Griffiths from the USA. He has already published a paper on an amplifier from 160 to 183 gigahertz with almost a quarter watt of output power, with power added efficiencies of around 7.5 and 9.5%, and a gain of 21 dB. And then he also published a paper 2 years later for a PA from 150 to 175 gigahertz with 30 dB of gain and more than 20 dBm output power, with even higher power added efficiencies of 12.5 to 16.2%. And this paper here is from ETH Zurich, and they are demonstrating a single transistor amplifier with more than 10 dBm output power and a power added efficiency of above 38%, which is the current record. At the bottom here, you can see one of the chips from Zach Griffiths. As you can see, and also see the dimensions, it's quite large. But again, at these high frequencies, it's very difficult to achieve high output power. So that means you need a lot of stages, need power combining, and also takes up space. Now to come to the development of indium phosphide chiplets at FBH. We have here an in-house technology which is running a triple meso indium phosphide DHPT process featuring 3 different emitter widths of 850, 700, and 500 nanometers. And their FT and Fmax values are above 300 gigahertz. So obviously the smaller nodes are achieving higher FT and Fmax values, while the bigger nodes are a bit more stable and able to achieve higher output powers. There are also aims for further node downscaling, so for example to 400 nanometers, which then requires also another design of the epitaxy, but that's a different topic. Together with these transistors, we also offer PN diodes based on the base collector epitaxy on the same stack. And there are also passive elements like semiconductor-based thin film resistors, silicon nitride capacitors, and also nickel chromium resistors. We have a metal stack consisting of 3 gold metal layers for routing. And there's also the possibility to make the chip usable for heterogeneous integration with silicon-based CMOS or BiCMOS circuits. And on the right, you can see an exemplary image of a indium phosphide HBT device. So some previous results from colleagues of mine are presented here. For example, a power amplifier from 140 to 220 gigahertz with up to 30% PAE and a peak PAE of 34% at 160 gigahertz. Another one is a D-band power amplifier with a saturated output power of 14 dBm and a power added efficiency of 10%. Then there's a dual stage amplifier with a very high bandwidth of more than 110 gigahertz and 24 dB of gain, which consists of a transimpedance amplifier cascaded with a distributed amplifier. And another work is a distributed amplifier with 175 gigahertz bandwidth, a gain of 12 dB, and an output power of 10 dBm. Then to the previous project that I worked on, this was about the development of a medical radar as part of the iCampus research project, which is also located in Cottbus, where my home university was. This research project is funded by the German government for structural changes in core regions. The goal was the development of a radar system operating in the ISM band at 61 gigahertz, which then should be used for contactless assessment of patients' vital parameters, for example, in hospital conditions. There are currently patient studies going on, and the project is close to finishing. Project partners are FBH in Berlin, IHP Microelectronics in Frankfurt, which they are making the main part of the radar, the Technical University in Cottbus, and also some people from Technical University of Hamburg. And our part at FBH was the development of indium phosphide MMICs for improved linearity performance in the receiver. So there we developed single components, like for example, a down conversion mixer or an LNA, and then put them together to achieve an integrated receiver circuit, which then should be integrated with a demo board and be compared to the silicon germanium approach used by IHP. And these ICs are currently in fabrication, and on the right you can see a layout picture of the integrated receiver. That's also a bit unfortunate since there are some delays in our clean room. I'm unfortunately not able to present measurement results. However, I can give you some simulation results to kind of highlight what we tried to achieve. Here you can see the comparison of some state-of-the-art works with 2 of my simulation results. The focus is on the P1 dB at the input, which is quite a bit higher than other published works, and hopefully I can, in the next time, confirm these simulations by doing some measurements and maybe present them at the European Microwave Week, but this still remains to be seen. These are, again, some layout pictures of the two mixer circuits. In the middle, you can see the respective mixer cores and then some matching and other layout structures around them. And now for the current project I'm working on, it's called Lausitz. So there's this terahertz component, and it's also part of the iCampus project. It started at the end of 2024, and currently we finished the part about system specifications and the system parameters we want to achieve. Overall, the goal is the development of integrated RF components and front ends for the use in sub-terahertz radars, together with assembly technologies, which also include different antenna configurations. Project partners are again FBH and IHB Microelectronics, together with Fraunhofer IZM, which is responsible for the development of the antennas. And our part at FPH is the development of indium phosphide power amplifier chiplets, which should then be used for heterogeneous integration with the IHP transmitters. And there our target specifications for the power amplifiers are more than 50 dBm of output power. Again, more is better. And certainly high PAE of minimum 15%, and an operating frequency at the upper end of D-band, which is around 160 gigahertz. And we then want to integrate these chiplets that we developed onto the 4-channel silicon germanium transmitters. And as a short conclusion, as I've mentioned, the physical properties of indium phosphide offer some advantages compared to existing CMOS technologies, which then introduces a promising technology platform for future applications demanding high output power and high efficiency at very high frequencies up until the sub-terahertz regime. And since it's possible to integrate these with CMOS and bi-CMOS circuits, you can also design more complex systems where you just use the indium phosphide chiplets for very specialized applications. And a hopeful increase in technology readiness and further process development will make these technologies more accessible and even more powerful. With that, I would like to thank you all for the attention. These are some of the references that I used so that you can maybe see them in the video later. And with that, I would be ready for some questions if you have some.
Yeah, thank you, Paul, for this very, very interesting talk. Yeah, to all participants in the audience, feel free. You are highly welcome to write your questions again using the Q&A or chat panel. And while you're surely doing so, I'd like to ask Paul, what about bandwidth, so to say? So a lot of interest is in moving to higher frequencies to get really wideband systems. How do indium phosphide components, power amplifiers perform in this sense compared to silicon germanium, for example, or to gallium nitride?
So as I've tried to show with two of the publications from my colleagues, you can see that it's possible to achieve high bandwidths, like, for example, 100 gigahertz, which could then be used to, for example, use these chips in fiber optic transmission to integrate them with optical components made by another company. So it's possible to achieve high bandwidth if your application demands it. It's just I would say it's depending on your design, but I can see it's a bit general.
Okay. Yeah, there's a question. Sorry if I missed this, but how does the thermal expansion coefficient compare to silicon? I'm thinking in terms of 3D heterogeneous packaging. Can you comment on that?
I think I'm not too much into this part of the research, but some of my colleagues who developed the integration process, they made some simulations on this, and it leads to, so this heterogeneous integration works by having some pillars on your indium phosphide chiplet, and then putting it in a flip chip approach onto the CMOS carrier, which obviously increases thermal resistance. And it also leads to higher temperatures, but we didn't really see a dramatic increase. So it's all designed in a way that you have kind of enough pillars to also support some lower thermal expansion or like lower thermal resistance. So it's not really a problem, I would say. However, in that regard, I maybe would refer you to the paper made by my colleagues about the integration process, which I think you can find it in the references. And if you want, you can also write me an email and I can send you the paper or send you the contact to my respective colleagues.
Okay. Maybe another question from my side. So when you're doing the power amplifier, for example, I suppose that's one of the last stages before, yeah, your signal is radiated by an antenna or something, right? So what are your plans there? Do you want to go off chip again by bond wires, or do you plan to integrate antennas in the indium phosphide technology on chip level again?
Again, I think the current plan is to then go off chip again, since we already have the flip chip approach. We are on the silicon germanium anyways, and maybe we're integrating the antenna on the silicon germanium chip. However, I think it's also possible to use indium phosphide for the antenna. I just don't know about its since it's a bit more brittle than other materials. If it's a good way to, for example, use it for antenna arrays, because maybe the stress of the metal would kind of have some negative impacts. But since the antennas are not really part of my work, that's a bit far out of my scope.
Okay. There's another question, again, regarding thermal issues. Are there any thermal issues when using flip chip for indium phosphide transistors? Degradation of the transistor, for example?
Yes, obviously, since I already mentioned, the thermal resistance gets a bit worse. So you have higher temperatures operating at the same power levels, which means you should be a bit more careful when designing your device or your circuit regarding operating point and everything like that. So like looking at the load line, so that you don't thermally overload your transistor and it's burning. But other than that, it's just similar to operating it in a normal way. Maybe you can kind of, I don't know, visualize it as like operating in a higher ambient temperature, so to speak, which is then putting some minor limitations on your power budget.
Okay. Yeah. So if there are no further questions, I'd like to thank you again, Paul, for giving us an insight into your work. Thank you to all the participants as well for being here today. Thank you to Aaron in the first part of our webinar today. I'd like to again invite all of you to submit your abstracts to the European Microwave Week and to the future Tom Brazil Award installment. So deadline will be 11th of March for both. Thanks for joining us and looking forward to meet you again in the next webinar or maybe in Utrecht. Thank you. Bye.
Thank you very much.
Thank you. Bye.